But he said this thing, which is stuck in my head, which is AI is a metal detector for hypotheses. So, as humans, we have tons of ideas. We have way more ideas than we have time to experiment on or investigate deeply. But when you have an advanced AI model at your side, it's this super smart thing that has read substantially every scientific paper that has been written in the last N decades across every field. It's infinitely patient. You can direct it mercilessly to explore the pros and cons of any idea that you have. You can even spawn 10 of them in parallel to explore all of your ideas at once and come back with the best ones, right? It is a metal detector for hypotheses. Which is why I keep coming back to this AI as a tool for scientists, to your question, Ed. Right? It gives scientists superpowers. The models are getting really, really good. They can do some things you can't, but also you're better at a whole bunch of things than they are. And it's really about the two together. It's a power tool that is ready to be guided by human expertise and intuition and judgment.
Yeah, I mean, I would say one thing I'm particularly excited about is, can we, with these tools, accomplish so much more in, science, Demis was mentioning in the keynote, or in, complicated engineering tasks that often would take, lots and lots of people, multiple years to accomplish? Could you actually have a system that, with the correct access to the right kinds of simulation environments and a learning set of agents that are trying to accomplish the task and break it down into smaller tasks, could you design an airplane in, 5 days instead of, many, many years? That would be amazing.
With the protein folding problem. And actually, they ended up becoming structural biologists, of course, in their career. And one specifically, I remember he was, every time we were in the pub playing table football or something, he would be talking about obsessively how this was the most important problem in biology. And more importantly, I think of it as a root node problem. Like if you could unlock that and find the structures of proteins, that would unlock whole new avenues of research. Things like drug discovery. Obviously, we're trying to push that, but also fundamental biology and disease understanding. So this was a problem worth really spending a lot of attention and time on because of the downstream effects that it would have.
But I think there's still a couple of things to do before realizing this magical promise of AI curing all diseases. One is we're still missing data. If you think about AI, it was able to be so performant on language because the internet already existed, so we could train on massive amounts of language. The same doesn't exist for biological data, and that's what I'm building with Chronicle Bio, as you know. Yeah. I think we really need to have great, rich databases of biological multi-omic data so that these models can be deployed on that biological information and help us understand biology a lot better. That's step number one. And then even when you accelerate, target discovery, drug discovery, etc., there's still a very big, regulatory roadblock. But I also think that AI is going to be able to accelerate that. I think AI is making any administrative task faster, so it should make the regulatory process faster. And I also think that AI is going to be able to model out safety outcomes without having to do, all of the current clinical trial infrastructure that we have to do. So I have a lot of hope that it will accelerate things, but I don't think we should expect that, AI on its own just magically discovers things. I think we have to make sure that we build an ecosystem around these AI models that facilitate discovery and accelerate the path to cures.
Now there are three ways of calling world models when it comes to spatial intelligence. One is what I call a renderer, when the model puts beautiful pixels on the screen, mostly like video generation model, and the consumer is mostly human eyeballs. And while the model commits to beautiful pixels on the screen, it doesn't necessarily commit to physics and dynamics and geometric correctness, because that's for just consuming, human eyeball consuming, not necessarily for computation and other tasks. Then another kind of world model is what we call a planner. That is more for machines, more for robots, where it outputs whatever the input is, the state of the world or the action, it outputs a correct action to take to the next step. And you see that kind of world model a lot for robotics applications, and you hear that in that context. The third kind, which I think is the linchpin of the three, is a simulator, is that it actually is consumed by humans as well as machines, is trying to respect the structure, the physics, and the dynamics of the world, and really simulate the 3D and 4D information of the world, as well as the semantic information. And the simulator could become a renderer. The simulator could become a planner. But this layer is a huge critical path, in my opinion, to unlock spatial intelligence. And that's what World Lab is working on.
We can ask the model to create what I call amazing videos or entertaining videos, which is media side. You make movies, you make shows. But you can also ask the model to make what I call boring videos, videos you don't want to watch. And videos you don't want to watch are 17 hours of objects being moved on a table. You probably no one here wants to watch that.
Sounds dreamy.
But there's one thing that might want to watch many hours of that, which is robots. So robots, we're creating videos for humans to watch, and now we're creating videos for robots to watch. And those videos are now becoming the ground kind of like truth on which models are learning around the world. So if you want to train a model to pick a bottle, you need to show it videos of that picking the bottle. Instead of you collecting and recording that, I can create a video, a synthetic video, a generative video of that robot or you picking the bottle. And I can then use that video to train this, and it works. And the robot, it's kind of insane that it works, but the robot is learning about a dream. It's learning about something that doesn't exist, and it's using that data to actually work, and it works. And we can deploy it, and it works, and it performs as it was actually watching real stuff.
And thanks to LLM coding, what took a whole team of research scientists at DeepMind and millions of dollars of research and compute can now be done for a few $1,000s of rented compute.
Okay, I guess we should first discuss how Go works.
So one big message from my talk is that if you want to use world models, do not work on video generation. This is a different problem, okay? If you want to produce cute videos, work on video generation. But if you want to control robots or industrial processes or understand the world, do not work on generation.
I think this is misunderstood. The safety requirements for AI are much, much higher for some areas like health than in others.
Yeah.
So today, if you consult ChatGPT, the general triage error rate will be 20 to 30%. That means you get the wrong answer 20 to 30% of the time. Now, humans are pretty bad at triage too, so you have to be careful. But when you add a health-specific system, and my son has a company that does that, but they use GPT-5, but layer on things on top, the triage error rate goes to 0.
Right.
Much better than human beings. And so I think in all these areas, if you're talking about national defense or healthcare or financial trading, you want to use these large models. All of them are essential. They're necessary, but not sufficient. You need additional things or various levels of insurance.
Doing technology change, doing world change is the only opportunity for greatness. Status quo, it's really hard to make a difference. And so I would deeply dive into the capabilities of artificial intelligence and use it in every possible way. And it's not just about mastery of science, but it's about mastery of using artificial intelligence in my field of science. Your purpose, if you decide to go into medicine, is to care for people. It's different than studying a radiology scan. Your purpose as an engineer is to either solve a known problem or discover problems that have never been solved, that are worthy to be solved. There's a fundamental difference between the tasks that we do in our job versus the purpose of our job. Everybody's purpose, every job's purpose, surprisingly, consists of tasks, but not defined by the tasks.